Sorry.
Okay. So today we will continue this very, very simple introduction to quantum mechanics, which is slightly different than what people go through really learning quantum mechanics for the first time, because I just want to stress the structure of the theory rather than technicalities of one particular example of it, which is usually the main object of the discussion in standard lectures and standard textbooks. In other words, I go as far as possible without specifying really what is this particular Hilbert space in which our system resides, and in some sense I'm not losing generality, because as I told you, all separable Hilbert spaces are isomorphic, up to dimensionality, of course. So, one of the last points mentioned a week ago was this well-known feature, well-known property of the self-adjoint operators, namely that if they commute, they can be diagonalized simultaneously. There is a common base. So today I will start reminding you how easily one can derive a general form of uncertainty relation. In other words, we will be talking now about non-commuting operators. So imagine that you've got two observables, namely nice and Hermitian guys. However, they are not interchangeable. Now they are Hermitian, yes, so A is equal to A dagger modulo this little mathematical subtleties that I've mentioned at the end last week. So suppose everything is fine. And as I say, this is not equal to 0. Now, if it's not equal to 0, then it is equal to something. Yeah? Then we call this something C. And I left room here for I. Why? Well, if I take psi AB phi, and then try to move A and B to the left, then of course I first have to move A and later B. So in other words, what does it say? What does it mean? It means that AB Hermitian conjugate is equal to B dagger A dagger. In other words, AB, if they are Hermitian, then its Hermitian conjugate is BA. Therefore, commutator because of this property, our commutator is of course anti-Hermitian. It's not Hermitian. I mean, it's Hermitian up to a sign. Yes? If I take Hermitian conjugate to this guy, I know that these guys are Hermitian. First fellow will be B times A, and the second fellow will be A times B. So I'm getting minus the commutator, and therefore, if I put I here, then my C will be Hermitian. That is very simple. And now, our aim is to derive the standard general form of the uncertainty relation. And for that, we take a family of states this. Let's take operator A minus mean value of A in some psi times this psi plus I lambda times B minus mean B acting on the same psi. Okay? That's a very simple trick. I have one-dimensional family of vectors. If I would take scalar product of this guy with itself, then of course as any square of the norm, it cannot be negative. It cannot be negative. And of course I can compute it. What do I get? Well, I have to multiply this fellow by its conjugate, which is the same as the mean value of A minus mean A squared. I think it's obvious, yes? Well, this fellow multiplied by its Hermitian conjugate will have this I times minus I, which is plus 1, so it will be lambda squared, and likewise this B guys will end up to the mean value of B minus mean B squared. This, as we all know, is called the variance. This, as we know, is called the variance. And now the linear term in lambda, it will be what? It will be I lambda times two things. When this is on this side and this is on the other, and I put everything on one side, I will get here mean value of A minus mean A times B minus mean B. When this guy is on the other side, it will be minus I lambda times the same thing, but in the opposite order. B minus mean B multiplied by A minus mean A. And now, of course, it's simple. When I do this multiplication, then mean times mean will cancel with this, but also linear terms in mean will cancel because, well, because you see how it goes. What will remain is actually mean value of A, B minus B, A. And that's what we like, because that's a commutator, yes? So since this is a commutator, this is equal to IC, we've got finally that this 0 is smaller, not larger, than A squared plus lambda squared AB. And I will be with this C will make me plus lambda times mean value of C, and now standard reasoning. We've got a quadratic polynomial of lambda.
Should there be minus lambda C?
Maybe minus, but that doesn't matter, as you probably understand. Yeah. Yes, so it's so-called delta, as they call it. How is it called in English? This delta, famous delta of the quadratic equation.
Oh,
Wyróżnik. See, I don't know. Shame on me.
Characteristic polynomial?
Well, come on, come on. I'm not talking about any polynomial, I'm talking about delta. Okay, we know what I want to say, yes?
It's a good polynomial.
well, the square root is a polynomial.
I try to remember, of course, I should have known, but I forgot.
Oh, it's a polynomial.
Ah,
So
yes,
this
yes.
B square
Yes,
means
yes.
for...
Never mind, okay.
And you know, this is so-called B square, as they say, minus 4 times A times C, yes?
It's a polynomial. Kind of.
It's a C square minus 4, this delta A times delta B. Now, this is supposed to be bigger than, I'm sorry, smaller than 0, yes. Smaller than 0. Then, of course, what we get is that square A times square B must be bigger or equal than in C divided by 4. Yes? That's the standard form of this.
Discriminant.
Yes, discriminant. Thank you. So we all learned. Discriminant. Actually, what was floating in my mind was determinant, but that is not. Okay, so the next, still very general point without specifying any particular operators. The next thing is so-called pictures of the, pictures in quantum mechanics. So we already said this last week, that time dependence of the vector is given by what is called the Schrödinger equation, and that this has a formal solution like this, psi of 0. I sometimes write this cat, sometimes not. Doesn't matter. Yes, and this is the evolution, unitary evolution operator. But this way of describing the dynamics of a system in quantum mechanics is only one possible. There are many others. And if we describe the evolution this way, by understanding or assuming that our states travel in the Hilbert space while time is progressing, that is called the Schrödinger picture. However, if I say the following, if I am interested in the way mean value of some given dynamical operator changes in time, then using this Schrödinger picture, I can write it this way: e to minus I h bar t over h times psi, then a e to minus I, I'm sorry, this is minus here, ht divided by h bar times psi, and of course, taking this fellow here, I can write like this, e to I h t over h bar a, e to minus times psi. And of course, what I see is that instead of considering states to evolve, I could equally well say that no, my states are not changing in time, but my dynamical variables do change in time, yes? And this is called, so this would be Schrödinger picture. And if I say psi constant, but A Heisenberg sometimes of t is equal to e to I h t divided by h bar A times e to minus I h t over h bar, then if I assume that my operators are changing in time, then I am in what we call a Heisenberg picture. As you probably can guess, or even more likely you know, there are infinitely many possibilities actually, because one could split this evolution operator into some parts, and one can apply one part to the right, in other words, to the state, and another part to the operator. So there are something. So there are many ways of defining intermediate type pictures that lie somewhere between Schrödinger and Heisenberg. Now, of course, this is some kind of the formal solution for the evolution equation, very much like this is the formal solution to the Schrödinger equation. Typically, when we do something, solving something, then we like to not to deal with such a formal solution, but rather with a differential equation. And of course, it's very easy to derive out of this a differential equation, dA Heisenberg by dt. Well, there are two terms. We have to differentiate here and then differentiate here, yes? When I differentiate here, then what I will get downstairs will be this guy on the left. And if I differentiate here, I will get this guy with a minus sign on the right. Whether here or here doesn't matter, because the h commutes with its function. But of course, it's nicer to put this derivative on the right, because in both terms, in the middle, I will get again my Heisenberg picture solution at time t. So in other words, it is the same as I divided by h bar, and here just a commutator of a Hamiltonian with operator h. Now, very rarely, this Heisenberg picture is really useful, but sometimes it is. And almost trivial example will come towards the end of today's lecture. However, from the conceptual point of view, it's very nice. It's very nice to understand that this is the equivalent formulation of the dynamics in quantum theory. Why? Because I can probably safely assume that all of you went through a very reasonable high-level course in classical mechanics, and you probably know that in classical mechanics there are many different equivalent ways of describing dynamics, and one of them is with help, well, first canonical formulation, and second with the help of Poisson brackets. Now, if this is the way you describe dynamics in classical physics, then your equations would look almost identical. Of course, in classical physics, there is no room either for I nor for h bar. But if you just remember to replace commutators by Poisson brackets, which, by the way, obey exactly the same algebraic properties, then this is just the same. It's not really any proof of anything, but it's just remarkable that in such a fundamental way, there is this very close link in the formalism. Okay, so this is my next remark for today. And still in the same vein of going relatively quickly through the fundamentals, let me tell you again in such a general frame about the density matrix. In other words, about the mixed states. Mixed states. Okay? Well, in many ways, we understand that in this quantum mechanical description, in which we do not know exactly where the particle is, what's its velocity and angular momentum and spin and whatnot, that we have to deal with these probabilities of finding our system in some given state. Then, in many circumstances, we would know even less. We wouldn't even know the wave function or the state vector, but we might only know, perhaps, that the state vector with some probability could be in psi I, different orthogonal, orthonormal states. The most typical physical situation in which we are bound to use such a description in terms of this distribution of probabilities of being in various states is when our system talks to some other, usually large system. If our system is just a subsystem, and for the whole our system plus the environment, perhaps it is in a very nice single state in this huge Hilbert space. However, eliminating variables, eliminating degrees of freedom of this environment, we are left with only partial knowledge of the state of the subsystem. And then this description in terms of the probability distribution of various wave functions is appropriate. Now, we of course know, we remember that if we have some state I, then mean value in this state is of course this product. That's fine. So now, if we have distribution, many orthogonal states with a probability distribution pi, which is nice because it sums to unity, so we are certain that we have some state, but we don't know which one, then I think it is absolutely obvious that if I multiply these guys by pi and sum over all these states that are perhaps present here, then that I will get a reasonable definition of this generalized mean value. Yes? I just have to take into account the fact that with probability pi, I've got mean value A in Ci.
So I cannot we define the total wave function as sum of those psi i's with square roots of pi's?
No, no, of course not. Just because in most mean values there will be cross terms. This would not reduce to such a simple formula, right?
Yes, yes, yes.
Unless, of course, these states are eigenstates and then orthogonality would reduce everything. But if not, then of course there would be mixed terms. Okay, now, as I say, these guys are assumed to be mutually orthonormal. However, of course, not necessarily complete, not necessarily form a basis. For instance, it could be infinitely many-dimensional space and maybe only 2 or 3 p's are non-zero. Nevertheless, I could extend this to infinity by, of course, assuming that in all the other directions, given p is 0. So I can add a lot of zeros. Why is it nice to extend it? Well, because if you do so, then operator rho with A, where operator rho is the sum over all I, pi, psi, psi I. So these are projections on each direction. So this way, this natural expression for the mean value turns out to be also nice geometrically because it's a well-known, well-defined trace operation for rho times A. Now, if I look at this form of rho, then I can check that it has three nice properties. First, rho is Hermitian. Well, indeed, if I Hermitian conjugate, then these psi's will be inverse, but they are identical. But here is psi, and here is the same psi. So of course it is Hermitian. Second, it is what people call non-negative or positive, non-negative. What does it mean? Well, it means that all the eigenvalues of this density matrix are non-negative. Of course, we see it. This is the decomposition, the spectral decomposition, yes? And these are the eigenvalues. From the very beginning, of course, they were assumed to be probabilities, so they are, of course, non-negative. Many of them could be zero, but certainly non-negative. Finally, if I would take just a trace of rho, then what I have to do, of course, I have to sandwich this in some basis. In particular, I could take the same basis here, and then, of course, I will get that this trace is just a sum of pi, and this was, if this was a legitimate probability distribution, then, of course, it must be. This is set of three properties of what we very quickly introduced here. But one can, in the books sometimes, it is stated the other way. One can start with just definition of some given operator rho by these three conditions, and then one can travel in the opposite direction. Of course, if this is nice Hermitian positive operator, then I can always diagonalize it. And if I diagonalize it, then, of course, then the mean value can be computed with the eigenvalues. So it goes both ways, yes. Fine.
You assume that the i's are orthogonal.
Yes, from the very beginning I said that they are orthonormal, but not necessarily complete. Yes, it could be only a few of them, but I can always extend this to the whole basis. Right. Okay, now they are even orthonormal, assumed to be
Since
orthonormal.
they are orthonormal, we can construct total psi, right?
Of course, many psi's we can construct, but rho is operating or is defined under completely different assumption. Namely, that this is not the combination, that it's a mixture, that it's only, that is either psi1 or psi2 or psi3 with probability p1, p2, and p3 without any interferences.
But if you assume that all those psi's are orthonormal, then
No.
what result would be different?
Oh, for instance, just as I was saying, if I would take combination with non-zero values, and if I would take operator A, which is not diagonalized in this basis,
okay.
then in the mean value there will be cross terms, right?
Yes.
While if it's a mixture, it's a very, it's a simple but very important question and very important distinction. Mixing has direct classical correspondence. In classical situation, we also might have limited information about the positions and momenta of a particle, and we can work in the phase space by using some kind of a probability distribution. Yes. On the other hand, in classical physics, there is no room for superpositions. There is no this structure of linear space and then squares of products, scalar products that are a link between this and observed quantities. Yeah. So it's very important. Now, what is, of course, if our system described by the density matrix, so described by perhaps a mixed state is mixed if more than one p is different than 0, right? If only one p is 1 and the others are 0, then of course we are back to the beginning, to the pure state. There's only one wave function. Okay, so if we have a mixed state, then we can ask yourself how it evolves in time. And of course, this is very simple. Our density matrix rho at times t will be a sum pi times evolved these psi guys. Yes. Now, I'm sorry. Now we know that this is e to minus I h bar h over h bar times t times psi I of 0, and this is the same. So we can pull out this guy on the left and this guy on the right, remembering that this was conjugate, so there will be change of sign, and rho of t will be equal to e minus I h t over h bar times rho of 0 e to I h t over h bar. It looks very similar to this Heisenberg evolution of the operators in the Heisenberg picture, but please note that signs are different. In the Heisenberg picture for the operators, I had plus here and minus here, and here is the opposite. Why? Well, because this evolution equation, this solution to the evolution equation, is actually a part of the Schrödinger picture description. Yes. We are evolving the state. Now our state is given by the density matrix, and that's how it changes in time. Surely, again, this is some kind of integrated result, and it's very nice to know what is the differential equation satisfied by this. Now, if I also write like this, then I get rho h almost identical as the Heisenberg equation, but again with a minus sign, or in other words, with a Hamiltonian placed in the in reverse order. It's very easy to make this small mistake by not noticing that this is the Schrödinger picture evolution. Good. My next point will be small remark, but very important. Symmetries and conservation laws. Well, in functional analysis, there is a well-known and beautiful theorem which says that there is a one-to-one correspondence between self-adjoint operators and unitary operators. So, and the relation goes like this. Every unitary operator has this form where if U unitary, then A self-adjoint. It is true even in this case of infinitely many-dimensional Hilbert space with all these unbounded situations. Now, unitary operator can be always defined in the whole space. It is bounded clearly because it's eigenvalues. If A is Hermitian, so A's eigenvalues are real, then eigenvalues of U are modulus 1. Yes? So if you have this eigenvalue modulus 1, then whatever state you take, apply U, write this state as the combination of eigenvectors, you will get new coefficients, expansion coefficients, which are just little rotations of each coefficient. So squared and added, they are always getting exactly the same result. Yes? It's, in short, it is the same as saying that U, if U is unitary, psi, U psi is equal to psi psi. For this reason, U cannot take you out of the Hilbert space. While A can, and that is often the case, and last week I was trying to persuade you that this is really even fun to discuss. Yes? Good. Now, quite often it is nice to pull out in this expression without changing, without reducing a generality of it, some coefficient, just because for many unitary operators we are really physically interested in the whole family of them, one-dimensional family of them, defined, I mean the family, I go from one member of the family to the next by changing this parameter A. Now, U, this unitary operator, which is defined as unitary by this expression, may sometimes leave Hamiltonian of some problem invariant. So sometimes U times Hamiltonian times U is equal to H, which written with the help of this fellow is the same as saying that expectation value of a Hamiltonian in the rotated state is exactly the same as the expectation value of unrotated state. If this is so, then U is called a symmetry. If this is so, then U is a symmetry of a Hamiltonian. All right. So, if I now take this form, in other words, if I write my unitary operator with the help of this Stone theorem, introducing explicitly A, then I will get something like e to I A times Hamiltonian e to minus I A equal H. So this would be the same condition written in terms of my A. Well, if so, then I can now differentiate both sides of this expression with respect to A. On the right, no A. So on the right I'm getting 0. And on the left, oh, I'm getting my good friend Hamiltonian commutator, yes? Of course, I times commutator of A with H. Aha. Term which probably you know, such fellow A related like this to the symmetry is called the generator of this symmetry. So this Hermitian of self-adjoint operator, which is a generator of this family of transformations, this generator then, if this is a symmetry of a Hamiltonian, this generator commutes with the Hamiltonian. Ah, but you remember, in Heisenberg picture, the commutator of the operator with the Hamiltonian is proportional to the time derivative of this operator. Now we say that if something is a symmetry, then the generator commutes. In other words, from this, it follows that A is a constant. So, this is, in few lines, very important theorem or observation. If this one-dimensional family of unitary operators is a symmetry of the Hamiltonian, then the generator defined by this family is a constant of motion. Yes. Okay. So,
in Heisenberg picture, right?
well, being constant of motion does not depend on the picture, of course, yes?
I know, but
Because if this is so, then if I sandwich this again in some state, then I can pull back the evolution operators, apply them to psi, and time independence, as I proposed or postulated, will remain.
okay, but what I meant is in Schrödinger picture, every operator is constant, right?
Yes, but in Schrödinger picture, the wave vector will change. However, in such a way that the mean value will be constant.
Okay, so
That's, in other words,
So the sense is
being
that
a constant of motion is a statement which is picture independent. Yes. Okay, so yes. So now let's take an example. Our example will be, I say, 1D translational motion of point particle. Then you will not be surprised that in this case our Hilbert space is just the L-square integrable function over R1. So in other words, our states will be psi of x, which squared and integrated from minus to plus infinity give 1. Let's think of translations. Yes? So translation by A computed at x is the same as x minus A. So I've translated this fellow. I think it is obvious that the scalar product of two translated vectors is the same as scalar product of two untranslated, non-translated vectors. So this operation defined by this formula is clearly a unitary operator. Moreover, it belongs to this family of operators which are characterized by the shift A. I can shift by little, or I can shift by little more, and so on. Let's try to figure out what is the generator of translations. Okay? To this end, let me take this psi of x minus a and expand it in a Taylor series with respect to a around psi of x. Yes? So we know how it goes. It is psi of x plus, or maybe minus, a over 1 factorial, which is 1, times derivative of psi of x with respect to x, plus, and so on, which is the same as saying that this is action of a sum over I from 0 to infinity, 1, or maybe n, I would like it, 1 over n factorial, yes, a to the nth power times minus d by dx to the nth power acting on psi of x. Do you agree that this is a compact way of writing the whole Taylor expansion? Sure it is. Okay, so, but this, when I look at this fellow, it is nothing else but symbolically the exponent, yes? This is about the same as saying that this is e to minus a d by dx times psi of x. You agree? Sure you agree. So now, if I write here I, and here 1 over I, and go back to my, I had minus, okay, go back to my general definition of the generator. Well, then what I see is that this generator for this thing must be proportional and to derivative with respect to x. By integrating by parts on the full line, we immediately check that it's Hermitian. It has a nice extension, unique self-adjoint extension. It's excellent operator. Now, again, we can invoke our knowledge of classical mechanics. And there, when studying canonical transformations, the same word generator, term generator is used. And perhaps some of you will remember that the generator of translation is a momentum of a particle. So what we found out by this little 1 line or 2 lines of calculations is that in quantum mechanics, it would be reasonable to call this fellow a momentum. Well, not exactly this fellow. Why? Because if I would choose this as a momentum, then dimensionality will not fit. Yeah, it would be 1 over centimeter, 1 over this in SI. And what I want for momentum is gram, kilogram times meter over second. It's easy to see that dimension, from the dimensional point of view, what's missing has the dimensionality of either angular momentum or action. And of course, H bar comes to mind, but only, it cannot be derived here, but only by remembering that H bar is just this constant which is missing here. Yes. The value of this constant is that one needs here for the proper definition of momentum, a constant of the dimensionality of action is actually obvious. So, as you know, this is not a big secret. This is a nice momentum, a correct operator that corresponds to momentum. It's widely used, we know. Almost immediately we can remember that, of course, it is, it does not commute with the position. Yes. What else do I want to say? Yeah, and the commutator is IH bar. So there is, of course, uncertainty relation with the product of the variance greater or equal to H bar over 2. This, I think, everyone knows, and I don't want to spend much time on that. Now, let's look closer at perhaps the most familiar example of quantum mechanical situation, which I already alluded to, introducing this momentum operator. Namely, translational motion of a particle, maybe in 1 or in 3 dimensions. It almost doesn't matter. So our theater, so to say, consists of rays, as people call, wave functions of real variables, square integrables, and with the square integrable and with the proper value of the scalar product, or norm equal to 1. Now, it goes without special explanation that if this is really a position, then the position operator should be just multiplication by x. I already mentioned last week that it's one of these nasty unbounded operators, but it's good. Certainly it is Hermitian. One can shift x as a real quantity in the scalar product, yes. I should add something that everyone knows. The scalar product here looks like this. So there's a phi psi, yes. And then, of course, if I would plug in x here, then I equally well plug it here because it's a real thing and can be shifted from one argument to the other. So it's a good operator. It has all the right properties. I even mentioned last week that we know what are these operators' eigenvectors. Namely, if I act with this operator and ask what's the eigenvalue y, then of course this stupid equation is immediately solved by a delta of x minus y. Y can be anything from minus to plus infinity. In other words, it's an example of unbounded operator with fully, completely continuous spectrum. If so, then eigenvectors are not normalizable. Indeed, square of delta is ill, cannot be integrated. On the other hand, if I take these so-called generalized eigenvectors that correspond to two different eigenvalues, then it is just like this. So in other words, given this freedom of working with improper wave functions that stick outside of the Hilbert space, if two eigenvalues are different, they are orthogonal. Of course, we cannot set y equal y prime because then it would blow up. It would be infinity. And that's a characteristic aspect of this generalized eigenvectors. Now, remember, kind of a general postulate was that if I had operator A and eigenvalue lambda, yes, something like this, yes, then my state psi would be found with the eigenvalue lambda if I just compute the scalar product and square it. That's the probability of finding lambda. If I would measure quantity A in this state, yes, then this is the probability. Okay, now what happens if I compute such a product with my generalized eigenvector? Something very simple. It is psi of y. Look, this way, without making it a postulate, we have found Born interpretation postulate of the wave function. It is this fellow corresponds to this. So square of the modulus of psi y should be considered the probability of finding y value of a position. Well, you know, this is continuous variable, so it cannot be a probability. It is probability density. In other words, I have to multiply it by some dy to get a probability of finding my system in a little interval of with delta x, so delta y over y. So by admitting these generalized eigenvectors, one can somehow understand a little better where does the postulate, the relating wave function with the probability distribution, where does it come from? Good. Now next. Well, next is of course momentum operator, which we already derived or conjectured or postulated or something that we recovered up to a constant out of looking at generation of translations, yes? So we know that our P is equal h bar over I times d by dx. We know that. So now we again may try to solve eigenvalue problem. This is a very easy one-dimensional equation. Its solution for any p, again from minus to plus infinity, is of course psi p of x equal e to I, sorry, p over h bar times x. That is obvious. I left some room for the constant. Where does the constant is coming from? Well, it is coming from the theorem about inverse Fourier transform, which I will invoke in a second. And it is best to take here square root of 2 pi times h bar. Why? Because if I will take my psi p complex conjugate of x multiplied by psi q of x and integrate with respect to dx, then out of this calculation it is 1 over 2 pi h bar times integral over dx from minus to plus infinity of x of e to I over h bar x times q minus p. Now, you probably know that the Fourier transform of such exponential is a delta function, and this 2 pi h bar is just taking care of the coefficient. If you don't know this, then you perhaps should remember the theorem of inverse Fourier transform. If you write together direct and inverse Laplace transform and treat it as identity, because it should be the same for every function psi, then you will easily check that this is the same as delta p minus q. So in other words, again, these generalized eigenvectors of the momentum operator that correspond to different eigenvalues, if p is not equal to q, then they are orthogonal. But again, if I set p equal to q, then I'm in trouble. I get infinity, and that's one of the trademarks, so to say, of the unbounded operators, of p belonging to the continuous spectrum. Right? Now, what if I take now a scalar product of a momentum eigenvector with some function psi? Well, this is by applying what I was having here, square root of 2 pi h bar times, it's a Fourier transformation, px over h bar psi of x dx. Well, you know it from, not from high school, but from your early studies of quantum mechanics. This we call wave function in the momentum representation. Why? Very simple. Again, treating this as an example of this prescription, again, I project given wave function on an eigenvector, yes? Exactly as I was doing here. Then I'm getting probability of, again, continuous spectrums of density, of finding momentum p in my state psi. So in other words, from this again, very much almost well, identically as a moment ago with my delta functions, from that it follows that psi of p modulus squared is the times dp is the probability of measuring p plus or minus half delta p, say, in our state. Yes? So that's the momentum distribution. If this is momentum distribution and a moment ago I had position distribution, then if someone would ask me about variances or I don't know, some higher moments, then if I have a distribution, then all it takes is to multiply it by proper power, yes, of this quantity and then integrate. So really the distribution, this underlying probability density of momentum or probability density of position are just really giving me direct entrance to any statistical question concerning the state psi of x. Moreover, I can compute various objects, like for instance this psi of p, either taking this Fourier transform, or better, I can compute, say, mean value of momentum, say, either by taking Fourier transform of p times psi of p, or by applying Fourier transforms like this and applying this delta using position representation, as we call it. And now there will be this differentiation here. So I can do it either way, yes? And the same with position. Position is so easy to compute in the position space, and it requires some differentiation in the momentum space. So there's this reciprocity. Now, I want to show you something almost trivial. Again, with some hope that not all of you have seen this calculation. in standard texts, people often discuss the question of the spreading of the wave packet in the absence of any interactions. And in most cases, this is discussed on a specific example. Typically one solves, and it's not very difficult, but one solves the evolution of the Gaussian wave packet, and then this is checking what is the Gaussian, remains Gaussian, but acquires, well, first broadens, then acquires some phase factors, and then people discuss it and see how these guys spread. Then sometimes the question comes, are all the wave packets spreading the same way? And then this slightly embarrassing question if one is trying to solve this problem via this Schrödinger evolution. However, if you do it in Heisenberg picture, then it is very, very, very easy task, and that's what I want to show you. So, imagine that we've got a free motion in one dimension of quantum particle. Then, of course, the Hamiltonian is like this, sure. And we can easily write and then solve the Heisenberg equation of motion for these main two operators, namely for the position and for the momentum. Well, let's start with this, with the simplest. Means let's start with the momentum. You remember, any derivative, time derivative of any operator is just I over h bar times a commutator with a Hamiltonian, yes? Okay? Well, Hamiltonian is the square of p, so obviously it's 0. So this equation I know how to solve. This equation says that P of t is equal to P of 0. Very simple. Now, what is the equation for x? I guess you know. Of course, x dot is P divided by m. What else? Now, since we know, this should be, of course, evaluated at times t. But since we know that, that p is constant, then we can also integrate this one. I'm laughing when I explain this, because every child would know that the motion without any is uniform, yes, it's the constant speed. So then it is like p of 0 over m times t, plus, of course, initial. If you don't know what I'm heading to, you could think that I'm completely stupid because I'm trying to tell you trivialities. Almost. Why? Let's look at the variance of this fellow. So we compute variance in some state, yes? What it is? Well, as always, it is this initial state times x of t minus mean x of t squared times psi. Okay. What I do now, of course, I introduce here and here my solutions. And what do I get? Psi here, and then I will write everything absolutely explicitly. So this is d naught times t divided by m plus x x naught, I will write x naught as the initial value, minus mean value of p naught, p naught over p naught times t over m, and minus value of x naught squared times the sign. Now look, this fellow with this fellow squared will combine into the variance, initial variance of p naught. Yes. Now, this fellow with this fellow, when squared, combines to this variance of this fellow. Plus, there is of course cross term. And this is easy, of course, to compute. And let me write what I can get. What I get is d delta x squared of t equals delta x square of 0 plus t squared divided by m square times square of 0 plus t over m times x p plus p x minus 2 x p. Of course, everything is at 0. And that's it. Now what we see is the following. We see that, of course, for any wave packet, not necessarily Gaussian, if I wait long enough, then it will spread, because here I have t squared, here I have t. And if so, then of course this fellow will always win. So the distribution of the momenta, distribution of the velocities, is telling me how quickly this fellow will spread. I repeat, for any wave packet, not necessarily Gaussian or two Gaussians or Gaussian with a factor or something. But note that for short times, I should not forget this linear term in time. And this linear term need not be positive, it could be negative. These guys could be bigger than this. Why? How? Well, if there is sufficient correlation, so to say, between position and momentum. Therefore, quite generally, the delta x squared versus time would typically go like this. It's parabolic, but for a while, for some specific times, wave packets can shrink. And of course, with this well-known solution of a Gaussian, one can also see this. You can wait for the Gaussian to spread a little, and then reverse time, and then it will, of course, shrink back to the initial state, and then expand again. Yes? So in other words, this situation here is rather typical. It's not at all unusual. It could happen for many different initial wave functions. Now, after having said this, I like to finish with the description and not performing experiment that several times when teaching about it, I did perform in the classroom. But today I did not bring any matches. So there will be no experimental description of it. So imagine that I take a box of matches and throw them at some flat surface. And of course, different matches will be pointing in different ways, like this, like this, like this, like this, like this, like this. And then imagine that each match is telling me what is the velocity. Maybe all these matches are of equal length, so the magnitude of velocity is the same, speed is the same, but the direction is different. And then my progression of time means that after some unit of time, this fellow moves along its line and jumps here. This fellow moves and jumps here. This fellow moves and jumps here. This fellow moves and jumps here. Now what you see is that clearly just because of a distribution, some random distribution of initial velocities, my, so to say, wave packet, namely the waist, the size here, is increasing. It's the same thing in quantum mechanics. If I got my results out of just trivial solutions of a Newton equation for a particle without any forces, then it means that all this can be interpreted completely classically. No wave function, nothing. Moreover, negativity of this term and initial shrinking is also easily modeled here. Imagine that I did not do things at random, but I meticulously placed my matches like this, yes, and applied the same principle of dynamics. Then, of course, a moment later, there will be, yes, there will be almost at the same point. However, again, if I wait long enough, they will spread again. Exactly the same features as there are for the motion of the free motion of the wave packet in quantum mechanics. Who has seen this before? You?
Because you showed me.
Oh, yeah, I showed you some time ago, so I think, yeah. Well, I kind of like it, and I can tell you that in some sense this lecture is geared towards telling such anecdotes and such trivialities. In some sense, pulling part of the mystery of quantum mechanics out of it, yes. In standard treatments, so much attention is put at solving differential equations. And quite often this is absolutely not necessary. Of course, it's very important that we know how to solve differential equations. Very often we can even write papers out of ability to solve these things, maybe typically on the computer. But many notions, many fundamental aspects of quantum mechanics are so easier to understand with these algebraic tricks, various ideas like using Heisenberg picture for this motion. Yes. As a last remark, let me tell you that applicability of these classical solutions to the Newton equations or to the canonical equations is restricted, of course, but goes slightly beyond my free motion. If the Hamiltonian does not contain terms that are higher than second powers of position and momenta, then canonical equations, or Heisenberg equations of motion, if you want, are linear. If they are linear, then they have solutions the same as in classical mechanics. Therefore, things of this kind can be studied in slightly more general case. For instance, in the case of particle which is not free, but is traveling under influence of constant force, for there could be constant force, then momentum would change, but we could still write explicitly solutions to the Heisenberg equations for position and momenta, and things of that kind are also easily solvable. I leave this as a little exercise, as a homework. Yes, we do not have to come back next week with homework done, but you can maybe have fun checking if the spreading of the wave packet is actually any different for a particle moving under the influence of constant force. Yes. One more step of complication, if we've got a particle which is moving in the harmonic potential, on 1/2 m omega square x squared, yes, then this again, upon computing the commutators, will lead to the linear equations of motion. Of course, this time mixing p and x, but they are well known, we know how to solve them. We know that standard sines and cosines of omega t pop up in the solutions. So again, one can compute any evolution of any interesting quantity for the harmonic oscillator, also in quantum mechanics, without solving Schrödinger equation for harmonic oscillator. And just as we all know that for the harmonic oscillator, all this solution of the canonical equation are periodic, so periodic are those variances, for instance, as even without computing them explicitly, we can say right away, yes. Since x of t comes back to x0 after the period, oscillation period, and p of t comes back to p0 after the oscillation period, so do both variances. As simple as this, yes. And I think it's time to finish. I'm glad I see some of you for the first time. Hopefully not for the last time. Until the next week. I think you have to.
Yep.